So what I'm going to talk about tonight will be far closer to home than gravitational waves. The first story is about this new image of the Orion Nebula, which was released this month from the European Space Observatory. And this particular image was taken in the near-infrared, and I'll explain more about what we can see in this image. But what's special about this is that they're making use of a new camera that's on the VLT, which stands for the Very Large Telescope. Once you really start digging into astronomy, you find that there are a lot of somewhat silly acronyms or somewhat uninteresting ones. So let's just talk a little bit about the Orion Nebula before we go diving into this image. But Orion is a constellation that many of you are probably familiar with. It's visible in the winter sky, so it's not visible now. But if you wait another 6 months, right after sunset, you'll see it towards the south. And Orion has the 3 belt stars, and there's also the red star Betelgeuse that makes up its left shoulder, and also the star Rigel that makes up its right knee. And Orion is often depicted as a hunter, and hence you have like a club or some kind of weapon and a shield in the other arm. But there's also a sword that's often seen hanging down from Orion's belt, and it's in that sword that the nebula is located. So if we zoom in to that sword, and this is something, well, you won't be able to see something as glorious as this with binoculars, but you will, if you were to point a pair of binoculars or even a small telescope, you will see a small fuzzy patch. And this is a ground-based image, but if we go in and zoom in with the Hubble Space Telescope, this is, and what we're seeing on this screen isn't super high resolution, but you can find these images online pretty easily. And what we are seeing when we see beautiful nebula like this is, in this particular case, we're seeing star formation at work. And so behind the Orion Nebula is actually an enormous molecular cloud of gas, and I'll show some data showing that gas in a few minutes. But out of this gas is born stars. And so these stars light up, and the winds and the jets and the radiation from these stars actually starts to excavate out from the inside. And so what we're seeing in the Orion Nebula is that gas cloud with literally thousands, 10,000 newborn stars in here. But the radiation and the activity of these stars have basically blown out the surface of the cloud. And so we're actually able to peer right deep inside the cloud to see these stars. And the reason why you get this beautiful emission is due to the ultraviolet radiation from these stars. They light up, they ionize the gas, and we're basically seeing ionization surfaces on the surface of the cloud due to the UV light of these bright stars. So we can continue to zoom in. So what we're doing is you can see this sort of central region, and we zoom in through another Hubble Space Telescope image. And in this case, there are actually 4 bright stars, and those are the most massive stars in the Orion Nebula. All these stars are at least 10 times the mass of the sun, and in fact, the most massive one is actually a binary. And so I think the most massive star in there is at least 38 times the mass of the sun. And so all these stars, or at least those 4 stars, will blow up as supernova when they die in a few million years. And so those supernova explosions will further disrupt and destroy the cloud. But all along here are other stars that are not as high mass. They might be similar to the mass of our sun, which won't blow up in a supernova. But you also see a lot of nebulous emission, hence nebula comes from either the Greek or the Roman word meaning cloud, and hence it does look very cloudy. And this cloudiness is due to the gas and dust. The molecular clouds are actually, by our Earth's standards, very close to vacuums. They're actually harder vacuums than anything that we can create in the lab. But because these clouds are so big, even when you have 10,000 or even 100 particles per cubic centimeter, when you look through them, they're so voluminous that the gas and the dust in the cloud can block starlight. And so you can see that there are a number of stars that are visible, but in at least the visible part of the spectrum, the light that we can see with our eyes, there's definitely a lot of obscuring material all around the cloud. But if we were to go into the infrared, actually the near-infrared, and this is taken actually with the Subaru telescope, I think. Actually, no, this is from the European Southern Observatory as well. So this is sort of the same structure that we saw before. You can see this, this bar down here corresponds to this bar here, but there are far more numerous stars that are visible, and that's just because in the infrared and in the near-infrared in this case, the infrared light can actually pass through a lot of that obscuring dust that would normally block light in the optical wavelengths. And those four bright stars I was talking about is right here. And you can even see some other stuff going on. There's actually another really massive star that's completely hidden. We can't even see it in the near-infrared, but it's exploded, or it's given off this explosion from its surface. It hasn't blown up in a supernova, but you can see ejecta coming out. You can see it faintly in the red. So that's what this looks like in the near-infrared. And what I'm going to do is we're going to look at the Orion Nebula and this whole region in Orion sideways, just to point out what the molecular cloud looks like. So I'm going to zoom in again. And this is an image taken by an amateur astrophotographer. So here is the Orion Nebula, and this is in optical light again. This is in the light of hydrogen, around 600 nanometers. And this is another famous object. This is the Horsehead Nebula, which is actually relatively close by to the Orion Nebula, so you have to go a little bit to the north. But this star here and this star here makes up two of the stars in the belt, so that sort of orients you. And the third star is over here, so these are the three belt stars. And then this is roughly aligned, but not quite, so this is about as close as I can get. If you were to point at this with a radio telescope that was actually sensitive to the code molecular gas that makes up the giant cloud of gas that the stars are born from, this is what you would see. So the Orion Nebula is somewhere in here, and this is the cloud that the Horsehead Nebula is in. And so this doesn't look like much, but we're seeing roughly about 100,000 solar masses worth of gas in what we call the Orion A molecular cloud. And it's really only in these cold, dense cloud cores that parts of the cloud can actually collapse to form stars. So I actually have a simulation of what a cloud core that might be 100 times or 120 times the mass of the sun as it collapses to form a massive star. And what happens is that these clouds do have some spin or angular momentum, and that causes the equator to be denser. And so as the star starts nuclear fusion and it starts blowing out a wind or the radiation, it's easier for it to come out along the poles. And so you have lots of stuff blowing out in this direction, but not so much along the equator. And in fact, the gas can continue to accrete or fall into the star along the equator. So this is what happens with one giant star, but astronomers have also done computer simulations with the cloud as a whole, or a small part of the cloud as a whole. So this is a simulation that was done more than a decade ago. And in this case, they again start off with something spherical, but you can see that the cloud starts collapsing into more filamentary shapes. So it doesn't immediately collapse inward radially or all towards the center. And these individual dots or stars that are forming, and what's really interesting is that there's a lot of dynamics that occur where the gravity of the stars start affecting how they move relative to each other. And so you can see that in some cases, some of the stars, as they interact gravitationally, they actually get sent off. So they get expelled from this cloud as it's collapsing. So this shows how one cloud can, over a period of 10, 20,000 years, form lots and lots of stars. And that's what we see not only in Orion, but in lots of molecular clouds throughout our galaxy. We see these giant clouds forming thousands of stars. Now, if we go back to this particular image, this image is in the near-infrared. So again, we're seeing a lot more stars than we would have if we were just to look at it through with optical or visible light. And so not only are we seeing a lot more stars, you're also seeing through the cloud and seeing into regions that was formerly obscured when we were looking only in visible light. And there are still some regions like here and here where the cloud is still so dense and so thick that not even the infrared is coming through. And so just looking at a picture like this, you can actually, if you're well attuned to what is going on in images like this, you can sort of figure out what you're seeing. And so next, go ahead and kill the sound, because I don't think we need the sound for this. Okay, thank you. So right here, we're zooming around different parts of the image and then comparing what it looks like in the optical versus the near-infrared. And so you can see that there are a lot more stars that are visible in the infrared. And here in the optical, you're seeing sort of one surface, but as you peer through, you can see how complicated that cloud surface can be. And so even in the infrared, in some cases, again, there are edges to the cloud where the gas is dense enough that the infrared light isn't really going through. And the other interesting thing is notice these sort of scallop-like edges. There are edges of the cloud that are being eaten away by the radiation and the winds from the massive stars. And you can even see places where it looks like there's light coming from individual stars, and those are likely places where young stars are just starting to be born, and their winds and their UV radiation are starting to affect the surrounding cloud. So there we go. All right, so what sort of science can you do with an image like this, in addition, other than the fact that it's a beautiful image? Well, one thing you can do is actually to go in and count all the stars and to figure out, based on the amount of light that you're measuring at different wavelengths, to figure out the masses of the stars that you're looking at. And when astronomers do that, not only for the Orion molecular cloud, but for molecular clouds and for stars throughout the galaxy, what they find is that there is what we call the initial mass function, which is a mathematical equation that describes how many stars that you find in for each type of star. And so this is from a paper from 2001, Pavel Krupa, and what he did was he basically looked at lots of different prior studies, and he came up with his own sort of what he called the universal initial mass function. And what this is this tells you, so along the bottom is the axis showing the mass of the star, and this is logarithmic, and so what that means is that this here means a star that has the mass of the sun, a star that's a mass of 1/10 of the mass of the sun, 100th the mass of the sun, 10 times the mass of the sun, and 100 times the mass of the sun. And along this axis tells you how many of the stars that you'd expect. And this is also logarithmic, so even though it doesn't look like there's that much difference between down here and up here, for instance, we're talking about a factor of 100. So what this says is that for really large stars, so again, this is 100 times the mass of the sun, there are very few large stars, and as you go to smaller and smaller stars, you find more and more of them. And as you get to really low mass stars, you still find more and more of them. So typically, for let's say 1,000 low mass stars, you might find 10 stars that are roughly the mass of the sun, or 100 stars of the mass of the sun. And for the most massive stars, you might find less than one star that's supermassive down at this end. Now, there are also, if you keep going to lower and lower masses, there's also a category of objects called brown dwarfs. And these are colloquially called failed stars, meaning they're not massive enough to start hydrogen burning. But people are really interested in understanding whether this initial mass function continues to go up or whether it turns over like it does here. And one of the problems with trying to understand how many brown dwarfs there are is that they're really hard to see. And so what you would like to do is go to places like the Orion Nebula and count up brown dwarfs and to see if there is indeed a particular turnover or whether it continues going up. And in an earlier study from 2002 and 2003, they found that there was indeed this turnover for the brown dwarfs, but there was also this slight bump towards the end. And unfortunately, the authors of these papers weren't really sure of this particular result because their instrumentation wasn't sensitive enough to see lots and lots of brown dwarfs. So even though they see this bump, it's just based on very small number statistics. So for this particular work, what they were able to do, and this is kind of a complicated plot, but we're again seeing the initial mass function. So the most massive stars are here, and the least massive ones are down towards the right, and the brown dwarfs are over here. And what I want to point out are the green, the red, and the black lines. And so what they see is the hump that you saw before for the main, the regular stars. But what they also find are smaller humps for the region where the brown dwarfs are. So what's really interesting is that in addition to it falling off, as the stars get lower and lower mass, their numbers also get lower. But as you get into the brown dwarfs, there seems to be a peak in the number of brown dwarfs, and this peak is right at about a quarter of a solar mass. And so as astronomers figure out how stars form and they run computer simulations, part of their goal will be to try and match what is observed at the very low end of the scale. So that's one really important result from this particular work.